As if this thing called the wave function wasn't all mysterious enough already. Let's complicate it a little bit more. No, let's not. Let's try to simplify it a little bit. I like simple things. So, what's up with it? Well, if you watch the previous video on what the wave function tries to describe, you already know there's some integer numbers, some numbers that try to describe different arrangements, different places where those electrons can exist outside of the nucleus in a stable way, because of course we know that iron is very stable, or copper or gold or even hydrogen is stable as an atom or molecule. But where are these electrons going? They could be in level 1, they could be in level 2, they could be in level 3, they could be in level 4, they could be in level 5. And if that was all there was to it, it'd be pretty simple. And I might ask, what is the shape of that level? Is it like just spherically symmetrical around the nucleus? Some of them are. That would make sense. Because what's the difference between left and right and up and down and front and back? I don't know. But actually, there becomes more to the story when you're out to level 2. Level 1 is just really super simple. It only has the s orbitals, they're called. But level 2 is a little more complicated. It has s orbitals and p orbitals. And then layer 3 is even more complicated than that. It has s orbitals and p orbitals and d orbitals. And level 4 is even more complicated than that. It has s orbitals, p orbitals, d orbitals, and something else called f orbitals. And even within that, there begins to be some complication. Let's not worry about this m sub s thing for right now. It's true that electrons sort of spin like a top, and sometimes if these electrons are in the same orbitals, they have to be spinning in different directions because electrons are negative and they'd rather get away from each other. So there's something called the Pauli exclusion principle that says two electrons can't be doing the same thing in the same space at the same time. They have to be doing a little bit differently. They can't be in the same quantum state. More about that later, but we want to worry also about another number called the m sub l number. It's kind of an orientation number. How are these orbitals oriented in space? So level 1 is super simple. All it has is n equals 1 only has this spherical orbital. It's called the, so let's see, if n equals 1, then L can be 0. It looks like this. If n equals 2, that's layer 2. It has also another spherical orbital larger than this one outside of the 1s called the 2s. But it also has these things called 2p orbitals, and they're shaped like this. We'll say more about those orientations in a different video, I think. Oh, fiddlesticks. Hang on a second. Can I get rid of that? I hope I can get rid of that. Yeah, alrighty. Sorry about that. There we go. That's better. Oh yeah, what was I saying? So there's all kinds of different geometries that allow solutions to the wave equation. And as I said, layer 1 only has this. Layer 2 has this and this. Layer 3, n equals 3, has this one and this one and this one. And n equals 4 has this one and this one and this one. Okay, let's look at a summary of that. The first time I heard about this, I'm freaking out. What are you talking about? So level 1, so maybe you will be too, but I'm just saying I have to tell you about it at some point and start thinking about it, practicing with it. Layer 1, called n equals 1, has only an s orbital. It's called the 1s orbital. And that 1s orbital has no real orientation in space because it's perfectly spherical. But that 1s orbital can hold two electrons, one of them spinning one way, one of them spinning the other way. Same for the layer 2. Layer 2 has a 2s orbital, L equals 0. These are different, called quantum numbers, that describe the geometries and orientations. Geometry, orientation. This is still spherical, so there's no difference between the 1s and the 2s, except for the 2s is a little bit bigger and placed outside, nested outside and around the 1s orbital, which is also outside and around the nucleus. But level 2, as you see, n equals 2 has the extra complication of the p orbitals. They look like this. One of them is called 2px, one of them is called 2py, one of them is called 2pz along the x and the y and the z axes. but other names for them include, let's see, I could call it a 2p negative sub negative 1, 2p sub 0, and a 2p sub positive 1. That's almost never done that way though, actually. It's usually called 2px, 2py, 2pz in different orientations. This orbital can hold 2 electrons, each spinning differently. This orbital can hold 2 electrons, each spinning differently. And this orbital can hold 2 electrons, each spinning differently. So to summarize, so far, there's 2 electrons in the 1s, this shape. There's 2 electrons in the 2s, this shape also, but larger outside of it. 2 electrons in this one, and 2 electrons in this one, and 2 electrons in this one, although that's not always the order they fill in. We'll talk more about that later. Not in this video. In any case, each orbital, every single orbital, can always hold 2 electrons, even if it gets complicated like this, or like this, or like this, or even beyond this, even more complicated. Only 2 electrons can fit in any one orbital. That's the end of the story for excuse me. That's the end of the story for the n equals 2. But now the n equals 3 gets even a little bit more complicated. Layer 3 has a 3s orbital, just like the layer n equals 1 and n equals 2, and it's also spherical, so there's no orientation. It's symmetrical in space. And it's nestled outside the 2s, which is outside the 1s, which is outside the nucleus. But it still can hold 2 electrons. Similarly, layer 3 has p orbitals, just like the 2p orbitals. These are called 3p orbitals, except they're nested outside of, a little bit larger, higher in energy than those, than the 2p's. They're called the 3p's, the 3px, 3py, 3pz along the x, y, and z axes, perpendicular to each other. But again, each can hold 2 electrons, one spinning one way, one spinning the other way. But look at this, oh my goodness. Layer 3 has even more complication. It's called the L equals 2, also called the d orbitals. And we saw what they looked like, looking pretty complicated, like 2 electrons can fit here, 2 here, 2 here, 2 here, 2 here, and those are, let's see, that adds up to 5 d orbitals. Oh, do you see a trend? There's 1 s orbital, 3 p orbitals, 5 d orbitals. Guess how many f orbitals there are? Anyways, don't memorize these names. It's good to study the geometries of the d orbitals so you can notice them, recognize them if you saw the geometry, a picture of them. But in any case, one d orbital is oriented in this direction, one d orbital is oriented in this direction, one d orbital is oriented along the z-axis with a donut, one d orbital is oriented in this direction, one d orbital is oriented in this direction. And don't even worry about the orientation too much, honestly. But again, it's good to study the geometries and see if you could recognize them. Believe it or not, this comes to play in the periodic table. I think we better save this electron configuration notation for a later video. But we'll see that the s orbitals and the p orbitals and the d orbitals and the f orbitals emerge when we look at the periodic table and the patterns within. And this person took the time to write out for each element what the n, l, and m sub l, that should be m sub l if you could fit it in there, it's kind of cramped though, quantum numbers are for, say, hydrogen and helium and lithium and, what is it, beryllium? I'm losing my mind. And fluorine and neon and copper and zinc and iron. Oh my goodness, don't memorize that, but look at the pattern. Kind of interesting. Guys, thanks for watching. I'll see you soon.